I'm not sure when they're gonna come.
Okay, I'm going to hit record and I'm going to explain that one again. So
Okay,
we
yes,
talked
please.
about as the temperature increases, the gas molecules move faster. How would I know that? Well, things to note, and I'm going to go a little bit faster because I already talked to the kids in person here about this, and also you can hit pause on if you're watching the recorded video. More heat is more motion. That's actually the definition of heat. The molecules are moving or bouncing faster if it gets hotter. If it's a gas, then they're actually moving around faster. They're not just jiggling in place faster. So more heat is more motion. Motion could be called moving or kinetic. Kinetic is another word for motion. Kinetic, by the way, it's Ki, kinetic energy. So kinetic energy mathematically is 1/2 mass times velocity squared. I would write down those terms if you don't know what they mean. And temperature is the average kinetic energy, really, just converted into a scale like Fahrenheit, or God help us, not Fahrenheit, Celsius or Kelvin. Sometimes we can use Celsius in these, depending on the problem. So if something's at the same temperature, it has the same average energy per molecule. So I made up a problem. Gas A and B are at the same temperature. One has this molar mass, one has this molar mass. So they're both in a box, and there's a small hole in the box. Over the next, it doesn't even matter, half hour, which one escapes more at random, right? Okay, they're equal moles too, right? We have 1 mole of each in a box, the same number of molecules. Which one escapes more? Well, the answer, without even touching this, is the one that's going faster because it's banging into the walls and searching for the hole more times per second, isn't it? So whichever one is faster gets out of the box better, finds the hole better. Which one's going faster? Well, what else do we know? We know they're at the same temperature, and temperature is the average kinetic energy. So if they have the same temperature, they have the same kinetic energy. And this really does go somewhere in case this seems like a long way around. If this answer has to be the same for both, then we can tell something else. If they have a different mass, but you have to multiply these two together and get the same energy both times, then you have to have different velocities. If this number goes down, but you need to get the same answer, this number must go up. If this number goes up, but you need to get the same answer, this number must go down. So the one that's moving fastest is the one with the smaller mass if they're at the same temperature. So the one banging around fastest, sort of searching for the hole the most, is the one that is the least massive. So the A would get out the hole faster than B. In fact, this is very much what this is talking about, or the kind of things. As the temperature increases, well, okay, it's not the same thing, but as the temperature increases, the motion increases, right? The gas molecules move faster. So the molecules collide with the walls of the container more frequently. Since they're going faster, don't they bang into the sides more often, more frequently? And the speed at which they bang into the sides of the box, and the frequency, how many times per second, add up to making the more pressure. If you speed them up, they push out harder. If they bang into the walls more often, they push out harder. You can increase the pressure theoretically without increasing the temperature if you pump more molecules in without heating them. Now, before Chris can jump in and said, but I read that more molecules pushed into a smaller space does increase the temperature. Yeah, well, I said if.
So we assume it's an isothermic scenario.
I was just saying that it could be done. You could theoretically pump in more molecules and not let the temperature go up, and that would also increase the pressure just because there are more molecules bumping into the side per second, just because there are more molecules in general.
Yeah.
in real life if you start cramming in more molecules without a ton of planning, and I don't know anybody who bothers, the temperature will rise in the box. In fact, I have done this one and even shown kids, you do the opposite. Now run all that logic backward. Open a hole in a high pressure box, and what happens?
Could you repeat that?
Yeah, I have a high pressure gas in a box, right?
Yeah.
And I take a big spike and I punch a hole in the box. What happens?
The pressure releases.
Right,
rather
gas
quickly.
flows out. Okay, and the pressure goes
Down.
which means the temperature goes
Down.
right. All the opposite of what I said, right? Instead of, I said, if you pump gas in, the temperature goes up. So if you let gas out, the temperature goes down. And in fact, you can get a high pressure box, so to speak, if you buy the CO2 cartridges meant for BB guns. Stand it up, put a nail on top, hit it with a hammer, and the gas comes out very fast. And it cools down quite a lot. In fact, it will ice up. It maybe, I don't know. I haven't tried it in the Barstow area. This air is very dry. But I saw it done in Orange County, and it actually got ice on the outside.
Can we do that?
Where do I buy CO2 cartridges in Barstow?
Walmart.
There should be a place. It's freaking Barstow. Every bro, camo colored, off-road, gun shooting, fish gear toting thing should be available in Barstow, huh?
Yep.
Well, I'll try. So, describe 2 reasons why the pressure changes as the temperature increases. As the temperature increases, the motion goes up, right? So that's 1. Reason 2. Well, okay, if they move faster, they're hitting with more energy, right? And I'm going to put that in there. Move faster and have, that's supposed to say have, more kinetic energy. Is that legible? I don't know. Is somebody watching this on a phone?
Yeah, I am.
Well, I don't know. Can you read this stuff?
Yeah.
Okay. Actually, that reminds me, maybe I should go in and change this answer to be a little bit more detailed. It's not just that they move faster, it's that they have more energy to hit with. Yes.
If, like, I would take the actual exam, and I just wrote that they bump into each other more and harder, like kind of loose terms, would that still count?
I'm going to expect so. The good news is that the most of the free response stuff is not actually much of and describe. It's much more calculate. Here's what I've told kids, though. Make yourself undeniable. Keep shoveling information at them till you think, if they think this is inadequate, I just don't even know what to do with them. Right? If you got the time, throw in everything you can think of. Because here's the other thing. I think this is kind of, I'm talking about other people. I'm talking about the seminars that they have sometimes. We're going to examine the grading system. And I go, I don't care about the grading system. What am I going to do? Discover the exact line between 0 points and 1 point and then coach the kids to hit the exact line? What if the kid is wrong? And then they get a 0? No, make yourself undeniable. Land way over here, huh?
Yeah.
Just keep shoveling that information at them till they go, oh, good God, shut up. I mean, if you have the time, of course. So I try to avoid the conversation much on how much description do I have to give. Why make it a close call? But on the other hand, if you sound like you know what you're talking about, I would think usually you got to get it. So you do not have to put this exact phrase, obviously. If pretending that they want you to describe this more, just off the top of my head, more heat is more kinetic energy, which gives more energy to the collision with the box, and more speed creates more frequent collisions. Both of these drive up the pressure. I don't know how they could deny that. You know what? Actually, the frequently does not make the more force. The more force, in fact, now I really want to rewrite that. With more force is more back here. Although technically energy is not force. To be physics teachery for whatever good I am at physics teaching. The difference is, in case you care, you have forgotten about it because you've been dealing with it your whole life, but there is a pressure in your butt right now. There is a force in your butt. But you're not moving. So there's no work being done. So there is no energy being used. You don't have to exert energy to sit down. That's kind of the whole problem with, America sitting, right? It doesn't use any energy. There's a force. You can feel it in your butt, but there's no energy used. So energy and force are not the same. But if you're going to use energy, emotion energy, then you have a force. And we said kinetic energy, right? So if the gas molecules move faster, they have more kinetic energy. And that means they hit the side of the box with more force. And they do it more often. They do it more frequently. So the force really, I'm going to move up here with more kinetic energy and force. How about that?
If you have more kinetic energy, wouldn't that mean more force?
That's what I'm saying. Okay, to be extra picky, partly also because it's Chris, really, but well, I'm talking about pressure. I just realized I was about to say something wrong. Pressure is energy over time. And since I assume that the time of the touching of the box doesn't really change, if you have more energy, you have more pressure, which is
pressure also equals force over surface area.
Excuse me. Am I misstating this? You are right, definitely. Pressure is definitely, maybe, I'm going to say a few things wrong eventually. I mean, through the whole course, please catch me on things, right? Pressure equals force over area. That's very true. Which is why you can't cut the steak with your finger. The area is too big. You need a knife to get enough pressure to separate the muscle fibers.
Yeah.
You know what? I take it back. It is not pressure. It is
power.
It is power. It's just, in fact, I said a watt, and I was thinking, because I'm on this call, I had a brain spasm and just couldn't think of the generic term for watts. Power is energy over time.
And just to be like super extra picky, it's work over time.
That is extra picky because the units of work are the same as energy. Yeah. Work is measured in energy. Or I'm going to put or work, because work is measured as energy used. So same thing, essentially.
Yeah.
Energy used is essentially work. Work used is measured in energy, so no. I mean, I think I'm right on that one. Pretty sure.
Yeah.
Okay.
I was just saying that just to be like super extra picky.
I'm not even sure that it's different though. Okay.
No,
Did we
it's
beat?
not.
All right. Did we beat A part 1 to death? Anybody got a thing on A
No, I'm good.
or A part 1? So this. Oh, okay. This because here, this reaction works for B. So this reacts with that to produce that as represented there, which I mean is just a restatement. In fact, I would almost wish they didn't put that because they're just saying basically, look here, dummy. So, we barely mentioned this before. Delta H of reaction. Oh boy, how deep do we need to go in this? Not too deep. Okay. There's a whole chapter that deals with this in very detailed ways. For the purposes of this problem, so delta H is the heat of reaction. Yeah, this is the basis of like chapter 7, I think. Heat of reaction, by the way. And it's called enthalpy. And I do not mean entropy. And yes, it's confusing. Enthalpy. And I don't know where the roots are for that. I don't know what like Greek word this comes from or something. I've never looked it up. So if they say enthalpy of reaction, doggone it, they mean delta H. And not that you should know that yet. And why would you know that already? But I wouldn't be entirely surprised if they said that. So enthalpy of reaction would be delta H. And this little circle here means it's the standard version for that reaction if you run it in standard conditions, which doesn't apply much to this problem. I thought I'd mention it at the moment because we're here. And then what do you call this? Well, this is delta H standard, or even I looked up that name of that teacher in Massachusetts, and it's Mrs. Murphy. So I asked Mrs. Murphy, and she said that yes, sometimes people call it delta H naught for 0. So delta H standard though. All right, so if this is a negative, then the system is losing energy. The energy of the chemicals is being lost to where? Well, outside. As either heating up other molecules directly somehow, or dumping, realistically, I don't know if I've asked this. Also, or maybe even primarily, there's another question. Every year I get a couple questions that I realize I've never quite asked. As light, some things glow in the visible spectrum that human eyeballs can see, and many things glow in the infrared that you can't see. But the predator goggles or the heat source goggles that they give to the soldiers, to be, as Chris said, extra picky, you're not seeing the heat, and I'm being extra picky. You're seeing the infrared photons coming through the air and are caught by the cameras and the goggles.
Wait. So is there a way to actually see? I don't know. Is there an actual way to see heat?
Not unless you could get God's microscope and see the molecules jiggling.
Oh man.
It does work as if you're not being a giant AP Chem nerd like I'm doing right now, then what's the difference, right? It got hot, I saw it. Shut up, nerd, right? Okay. But I'm saying the hot thing, the hot object sent out, right? Infrared photons, because everything hot is trying to cool down, right? How does it do that? It dumps infrared light out, and with the right kind of camera, you can catch those photons just essentially kind of like your eyeball catches visible light. And then in those headsets, what they have is essentially like a computer program converter. If you are triggered by an infrared photon here in this portion of the camera, now please go display, please glow on the screen, right? On the screen, put glow here in human visible. So it translates the pickup of this to something that you can see.
Oh.
And
Mr. Slaney,
if it's getting more of them, it changes the color even, right? To more like red. So it even does a calculation on the number of them hitting the camera in what portion of the camera, so that you can get like, you know, blue fading to green to red kind of thing. What?
I know entropy measures, I'm going to quote chaos, but what does enthalpy measure?
So enthalpy, honestly, I don't even know why we bother. I personally, I mean, there may be a good reason, but for the purposes of this test, I just think it's just another word for heat or energy, heat energy, or just energy even. At least energy that is not the portion that is the entropy. How about that? And when I see heat energy, to be picky, like I say, I have a giant suspicion that when you make a chemical reaction and you take one of these and one of those are incredibly tiny, right? You make one of these,
yeah,
it's incredibly tiny. Well, how does it heat up its neighbors? I am gonna bet you $5 that really what it does is it shot out infrared light, which was immediately captured by the neighbors and made them jiggle more, so they got hotter. So it spread the heat. But how did it spread it? Is my question.
Oh, I was just going to say, wouldn't that be like shown because delta H is negative?
Right. So I was getting extra nerdy. How does it spread the heat is not a question on the test. Okay, but so I think it's by infrared light. And I could try to remember to ask Mrs. Murphy if she knows. But anyway, heat is coming out of the system. This is the point. Back to the part that will help you get something right on the test. The heat is coming out. So the heat is a product, huh? If you do this, does heat go into the chemicals or out of them? Out of the reactants.
Out.
Out. It comes out. It is produced then, huh?
Yeah.
So if the delta H is a negative, heat is a product.
And then it would be exothermic, right?
Exactly. And that is then, I've run out of room. Exothermic. I don't remember entirely. I think that does probably come up at some point. They probably do expect that you know that word. Let's put it this way. I wouldn't be shocked if they said this is demonstrated to be an exothermic reaction and expect you to go, heat is on the right side. And then you have to go on from there. Well, I'm glad we talked about this because there was a whole bunch of stuff. All right. In fact, we're only down here. All right. When this is injected into the container of that, sure, at some temperature, well, I don't know that that's important exactly, but I guess I'll put it in a box because I genuinely don't know. The total pressure increases. Well, yeah. If you take gas, as I said, and you pump in more gas, where's my, anyway, the temperature goes up. So kind of duh. Then as the reaction proceeds at 450 K, the total pressure decreases. Yes. This is the kind of thing they like. Explain this decrease in total pressure in terms of what occurs at the molecular level. Right. Okay, so if we assume that every molecule is basically the same size, this has more in it, I know. But seriously, the difference in size between this and that is so small that it can be effectively ignored. Is that note to self? That is probably a note to self. We assume that the gas molecules are so close to the same size that it's not worth discussing. They're the same size. Good enough. So if we ignore that this has 8 atoms in it and this only has 2, just ignore that. It's not worth discussing kind of thing. If that's true, then this side has twice as much stuff in it as that, doesn't it? Oh, yeah. I almost thought it wasn't balanced, but there are 5 H's, huh? 2 C's. All right. Because this has 1 particle, 2 particles. This has 1 particle. So as this reaction proceeds, is the number of particles in the box container getting greater or lesser?
Lesser.
Yeah, by a factor of a half, right? 2 become 1?
But real quick, what about the heat?
Right.
Well, do we just assume it's not enough to make the pressure higher?
It's not gonna, yeah, assume it's not enough. Yeah, basically. Not enough to compensate for the fact that it's going down to half as many molecules. Plus, they said, well, not only that, they said as a fact, the total pressure decreases. So I'm not saying that that isn't part of the thing that would be happening, but they did it and the total pressure decreases. So they're saying, in effect, hey, the heat is not enough to make up for whatever else is happening. The pressure still goes down. Does that work?
Yeah.
Okay. I got a text, just a moment. Okay. So it goes down. Well, if it goes down, and they're saying it goes down, dummy, it goes down, we did it, it goes down. Okay, if it goes down, then I guess Chris is right to think about, well, the heat would make it go up. Okay, but still overall it goes down. So the heat is not the main driving force here, right? Because the heat's trying to make the pressure go up, but in fact it actually went down. And so the answer is, and I didn't even read theirs, the number of molecules is decreasing as the reaction proceeds from 2 molecules of reactant to 1 molecule of product. And however they said that, I'm saying the same thing. Therefore, and if you want it, like I was saying, shovel information at them, right? Fewer molecules will hit fewer times per second or with less frequency, right? Don't they see frequency in here? Oh, you could say that. They didn't. You could, again, shovel information at them. Fewer molecules hits the walls with less frequency, which reduces the pressure. Some of the answers supplied by the workbook writers are so long that I just think no one's actually going to write that on the real test. It's a timed test and everybody's in a time panic. No one's going to write all that. 2 molecules, or you could even say moles, they would take that. 2 moles or molecules of reactant become 1 mole of product. Fewer molecules strike the sides with less frequency, which reduces the pressure. One of my phrases is, if they denied you the point on that one, I would fight them. I mean, like, I would be in a mood to like stand up and say, come here, I'm going to fight you. Come on, that's a great answer. It's the same thing as what they said too, basically. Should I repeat that for somebody though? Naomi and Annalee are still here?
Yeah, just to clarify, you said
Yep.
fewer molecules hit the wall with less frequency as the pressure decreases.
And so the pressure decreases even better.
So the pressure decreases. Okay.
Because again, and I know I'm saying it for the 4th time or something, 2 molecules turns into 1 molecule So there are just fewer molecules to do the striking of the sides.
Oh, okay. It makes sense now. Thank you.
By a large proportion. It's not like 7 became 6. That would be lesser. But by proportion, it's not near as good as 2 becomes 1, right?
Yeah.
The percentage drop is much better for 2 turning to 1 instead of like 8 turning to 6, right?
Mm-hmm.
All right. So anybody else on B? And then the dividing line here is there. So this is information about the answer for C. It is proposed that the formation of this, that this is the overall reaction. This is the proposed step, elementary step. Aha, look, rate determining step. And I told you they like that.
Mr. Sweeney,
Yeah.
this is kind of like a question I really understood. So I know that if the rate determining steps first, you just do the reactants in the
Yeah.
rate law. But why is it if there are steps preceding it, it's products over reactants?
Oh, well, for that one part, because, and I'm saying this only to say you might remember, not, hey, dummy, I told you once, because we don't do that in this class especially. It's really hard, right? Here's
Right.
fast and then slow, right?
Right.
Because the NO3 is being, from the fast step, is being supplied to the slow. Where is it getting the NO3? You didn't supply it. This is what you supplied, right?
Right.
Supplied by you is that stuff in the box. Where did it get NO3? It got it from the combination here, right? So
Right.
this supplies that. But because it's, we had it. Okay, go ahead.
Yeah, it just clicked. Yeah.
Okay, and just to go on though, what I said was that the fast step is going usually a good bit faster than the slow step. And real quick, this stuff will build up. You'll have more NO3 being made than you can have this stuff pick up, right? You're making 5 and picking up 2. This stuff builds up real fast, right?
Right.
At that point, they've got so much NO3 that it kind of doesn't know what to do with itself, and it starts running this reaction backward. Because this is a reversible reaction. You can make this, it can also fall apart. And you give it enough of this, and it will start falling apart. And you give it enough, and the rates of creation and falling apart will be equal, and you will have an equilibrium. That's literally what it means, right? It will run equally fast in both directions, at which point an equilibrium sets up the situation where you have the KEQ is true. And KEQ does involve the products. KEQ involves the products. A rate law does not involve the products directly. A rate law uses the reactants. The products get involved if the slow step is second. Everybody listening to this now or later, I would suggest finding these problems where the fast equilibrium is first or the slow step is second, same thing, well, however they phrased it, right? And do the mathematical substitution. Cover over the answers or grab a new sheet of paper, right? And do it again, because there's one, and not that, that's not what they're trying to show there. There's one. This page with the double bump graph. There's one. This is the real dinger right? We went around and around on this one because you have to substitute into your substitution on 3 and 4. If you can do those and go, do them all again, and if you can do those, then I think you got the point. And I can be helpful. And if anybody wants to talk to me singly outside of these sessions, that's fine. I am not going to let this class go down because of me. Doggone it, if I met somebody out, I think I said this, out of class last year, probably 30 hours herself. We'll make something happen. Was that good enough on that part? Chris, I guess you're the one who asked it.
Yeah.
Okay. Here, though, the rate determining step is the first step, so we don't have to do all this mathematical substitution. For the purposes of the rate law, then, the fast step can be ignored. So what's the rate law? Just ignore the fast step. It's this to the first times that to the first times k equals rate. That's exactly what I just said right there. What's an intermediate? It's something that's created and yet destroyed. That's created and yet destroyed. It's not here, right? That's created and yet used up. So they're both intermediates. And they're not in the full reaction back here because they're not at the beginning and they're not at the end.
Mr. Sweeney, if you add a catalyst in the beginning, would that be part of the equation or no?
Yeah, the catalyst is, by the way, and I don't know that this actually comes up, but since you brought it up, here's the main, I shouldn't put over this, is usually written over the arrow. Because it's not really a product and it's not really a reactant.
Yeah.
So if you have like platinum, they'll write it over the arrow, like note, like, hey buddy, also we did this with platinum. So when you think of us or you see our numbers, well, we did it with platinum present. That kind of thing. And a catalyst would be something like this. Just pretend, in case you care, if you want to jot this in. So we put in chemical A, right? And yet at the end, there's chemical A. So is it a reactant? Well, only sort of, not really. It didn't get used up, right? It's still present. Or even weirder, I have seen ones written out where A actually gets used up and yet is recreated. Like step 1 uses it, but step 2 creates it. And so it's on both sides again. So that's still a catalyst.
Mr. Sweeney,
Yep.
for their intermediate
Yep.
things, I know that C2H5 gets crossed off at the bottom of step 2 and the top of step 1, but there's another. Oh wait, no, never mind. I'm wrong. I take back my question.
Okay.
I didn't
All
see
right.
that.
All right. I was just checking if they put a minus there, but it turns out I colored over it. All right. Well, moving on. Anybody got a thing? Draw a curve. Now, they would just be in very rough figures. Notice there are no numbers here, right? Progress, this is time, by the way, essentially. I mean, how else are you going to measure the progress? I guess you could do it by molarity, but they mean time, essentially. And potential energy. So there is some energy in these chemicals. Yeah, that's the reaction we're talking about. Yes, Yeah, these chemicals. If they go through 2 steps, then they have to accomplish this, and then again, they have to accomplish another thing, right? So this is the thing about talking about these. I have to go back up all these things. I think we talked about it a little bit. To accomplish a reaction, what you have is the potential energy and then time or progress. It doesn't matter. Let's not argue about that. So my classic is burning paper. Maybe I said this, but I'm going to say it on the recording. So paper does not just leap into flame because it feels like it. You have it's sitting at some amount of energy, and it is not zero, otherwise it wouldn't burn. Right? There's some chemical energy in the paper. And when kids say, what do you mean? It just sits there. I go, well, does it set on fire? Yes. Does heat and light come out? Yes. Well, then where did the energy come from if there's no energy in the paper? I don't know. I didn't think of it. So there is energy in the paper. Okay, we'll just say it's here. I don't know, somewhere. It does not just leap into flame and release energy. You have to put energy in, and then at some point, you hit enough energy that it starts coming out and out and out and out and out, and it settles down at, I don't know, somewhere down here, right? For paper, it is, if you set paper on fire, you get something that is basically zero. Fire tends to suck all the energy out of this stuff.
Sorry, Mr. Swaney.
Yeah.
So the larger that incline part is at the beginning, the slower it takes, the longer it takes,
Right.
right?
That's their point here. Right. Also, though, the difference between these bars here is the energy of activation, or the activation energy. It's the energy you got to pump in to get the sucker started. You got to drive the energy from this point where it's sitting before you walked up to the part where it starts doing its stuff. But if you have to pump in more energy, shouldn't that take more time? And since we know this is the slow step, they're not going to say slow step. They're going to say rate determining step. But that's the slow step, isn't it? Doesn't it take more time? Yeah. Does it happen first or second? Duh, it happens first, right? So the first bump is higher than the second bump, and that's all they're really looking for. Oh, wait, there is one more thing. They're also looking for you end up below where you started, because they said delta H is negative, huh? So do the chemicals have more energy at the beginning or at the end? They have more at the beginning. So what they're looking for is pick a starting point, have the first bump bigger than the second bump, and end lower than where you started. Or even it's a multiple choice question. This is the rate determining step. This is the fast step. Which of the following 4 graphs could be the potential energy graph for this reaction? And you're supposed to say, rate determining, that's the slow one. It's the one that's going to need more energy. It's slow because I have to pump in more energy. This takes more energy than that one. So it goes high bump, low bump. Oh, and then they'll say, you know, this right also here. And so one of the choices for a multiple choice could be something like this. High bump, low bump, ends higher than when it started. That is called wrong because it doesn't end higher than it started. Because that's a negative number. Energy is coming out of the system overall. From beginning to end, there's less energy in the molecules now than when they started.
Mr. Swaney.
Yep.
This is part in 2.3 that I didn't quite understand. It was the kinetic energy distribution graph.
Oh, yeah. I have a feeling. Oh, these. Yeah, these.
Yeah, but the one below it.
Oh,
that
yes. I thought that's where I just realized. Yep. Those are confusing at first, at least. In fact, I have to stare at this for a moment. Here, this is the stuff we were doing before. Oh, also. Okay. This is the effect of, is that an F? A catalyst. And I have seen them ask questions that effectively say, do you know what happens with a catalyst? Like they give you graph one. The student ran a reaction, and this was the potential energy graph. She ran it again a second time, changing the parameters, and the second graph doesn't go up here; it goes little bump, right? What could be the reason for the change in the graph? And the answer is supposed to be she used a catalyst, because catalysts lower the activation energy. I would write that out. Catalysts lower the activation energy. Look. And to be picky, those guys are right. It actually changes the steps. They don't expect you to know what steps, but to be extra picky, they're right. It changes the pathway to the end reaction. It changes the intermediate steps, but those intermediate steps have a lower activation energy overall. So effectively, you get this. You get a lower bump if you use a catalyst. Okay, go
So
ahead.
the one below it then?
Yeah.
For energy distribution.
Yep.
Would that wouldn't be a catalyst? I know
No,
it
this is a
lowers.
completely different graph. In fact, it's so different that I'm having to stare at it again myself.
Okay.
I was just about to say, what are the axes? And then I had a blip and went, wait a minute, don't say it wrong. I'm not saying you were interrupting. I'm just explaining that, yeah, it's very different. And I haven't seen it in a while, and I'm having to actually think. The energy is this way, and therefore, yeah. So this is the energy, and this is the number of molecules. And I don't know why they didn't label that. I can't remember if they just don't label it. I think they might not. You're expected to kind of know, which I don't know, is kind of dumb. So number of molecules, energy.
Oh, what does the number of molecules have to do with anything now?
Right.
Is that
So
the number of molecules hitting each other?
the number of molecules that have a certain energy, right?
Oh, so wait, this is more like a histogram and not like one's dependent on the other.
You stumped me with histogram. It doesn't come up in this class. Stats nerd.
It's more like at one point in energy, it has a specific amount compared to another.
A specific what?
It's like when the energy is 5, the amount of molecules would be 10. But when the energy is 15, the amount of molecules would be 20.
That sounds like a regular graph to me. I don't know.
I mean, yeah, it is kind of a real graph. Yeah. It's a little different.
Okay, in my own words, let's see here. So what they mean is, use the dash line to indicate what happens when a catalyst is added. Because we said one way to view it is the activation energy goes down, right? Here's another thing. or this is the threshold energy. This is where the reaction takes place. That probably doesn't read. Where reaction happens. The threshold energy. So this is version A, right? This is version B, and version B has a catalyst. So B has catalyst. Is that legible?
Yeah.
Even on a phone. Okay. So let's just talk about the solid line. The number of molecules that have no energy is basically zero, right? No energy is basically no molecules. As you graph how many molecules have this energy, the number gets bigger and bigger and bigger and bigger and bigger. And at some point, of course, there must be an average. And the average is going to be the highest point. The biggest number of molecules that exist at any one energy is going to be the average. They're clustered in a sort of a bell curve around the average, right?
That kind of doesn't make sense.
No? Why?
No. So why must the high point be the average?
How could it be the low point?
I know, but why is it specifically the high point?
Night custodian Val, please call the front office at 2107. Again, Val, please.
It's the average is the average because so many molecules either have it or are close to it.
I know, but there are so many in front that wouldn't it be dragged up the average, so it'd be a little after the high point.
Hold on. It's a decent point. I think I just understood your point. You know, you may have found a flaw in their little graph. Okay, Smarty Pants. I'm gonna write that down on a think and maybe ask Mrs. Murphy question. Question 1 was, do reactions pass heat mostly by infrared, right?
Right.
Okay. Number 2 is on a kinetic energy distribution graph. Can the average not be at the high bump?
So wait, is
Okay.
the total area under that curve the total number of molecules?
Yeah.
Oh, all right.
But I see what you mean. If you take this area, it's greater than this area, and could the average be off the top of the bump? Could it be here?
Yeah.
Okay. That's a decent point. I don't know that they were doing that kind of thinking when they drew this, and this is one of the little, maybe this is one of those little hiccups that happens when you have, two guys who make a workbook. The reason I still like this workbook, despite stuff like that, is because the textbooks, if you get a college textbook that includes all these topics, it's 1.5 inches thick. You try to read it. I know what it's talking about mostly, and I hate reading it. Plus, they have the solutions, and the solutions have saved us so much time and effort. But you're right, you may have found a hiccup in it. I will think about it and or ask, okay? So here's the amount of molecules that can do the action of having the reaction happen, right? Here's this number. This is the number for version A. You add a catalyst. Well, first of all, okay. Oh, look, the catalyst is added and the temperature is increased. Yes. Okay, this is what I get for not reading. And you guys need to catch me. I'm sorry. I just, we've all got our weaknesses, and I read past the question. Usually when I'm getting it wrong or I'm not making sense, ask me if I made sure I understood the question. Please, for everyone's sake. The catalyst is added. What does that do? It backs up the activation energy to be easier to get to, right? Less energy is needed to get the reaction going, to make it happen if you add a catalyst. So this is the catalyst effect. The heating takes the number of molecules that have a certain energy and pushes it toward more energy, doesn't it?
Wait,
Yes.
ask that again?
If you heat it, the temperature is increased.
Yes.
You're pumping in heat. So how many molecules have this amount of energy? More than last time, right? More than last time, more than last time, more than last time, more than last time. And it pushes, remember, the heating is pushing things to the right, not up, because the up is the number of molecules, which doesn't change. So when you heat it, everything shifts. It kind of squashes everything to the right.
Oh. Okay.
Because remember, it's tempting, and I know I still get myself turned around sometimes, and I've gone over this workbook 4 times, and these things, I've seen these things before, but and every workbook or textbook has these kinds of things in it. It's tempting to say more energy up. No, more energy right. So the whole thing, the whole bump system shifts out to the right. So will this reaction happen easier? Yes. First of all, you heated it, and it would have happened more anyway, because more molecules have the threshold energy where the reaction happens. But if you added a catalyst also, then you scooted the amount needed back. So you had a double effect. So the number of molecules that will react went from here, right, to here, didn't it?
Yes.
So that seems like a lot.
Yeah. Well, yeah, it does seem like a lot. Mm-hmm.
What? So, oh yes, in this problem, sketch what would happen if you to the average kinetic energy and the threshold energy, if a catalyst is added, this scoots back. The temperature is increased. This bump kind of squashes down or to the right, and it spreads out more evenly to the right. Why does the addition of catalyst speed up the reaction? The activation energy is lowered. The threshold energy is easier to achieve. Now, I know I didn't say more molecules collide with sufficient. Oh, that is true. They love that phrase. More molecules collide with sufficient energy. Whoops, from. Whoopsie. Typo. To form the transition state. You know, if you really want to throw it in, I have a feeling are we getting to the end of people's brain power? It's okay. If I'm going to shovel all the information at them, I'm going to talk about something else. Can I throw in at least this last little bit?
Yeah. Yes, please.
Okay. Just for dumb diagrams, because I am no artist to say the least. I have molecule A and I have molecule B for just really obvious diagrams that even I can draw, right? These need to, B. These need to dock. Well, guess what? There's only one way they fit in the docking position, and butt to butt does not count, okay? There's only one direction, right?
Yes, there's only one direction it can go.
Not only that, but they have to bump together hard enough that they start exchanging electrons and start making shared pairs, which is covalent bonds, or whatever they're going to do. So they can't just lightly bump. You got to slam them together with enough energy to get this moving. I mean, to get the reaction to actually happen. If you lightly bump them, it won't count, and you will get nothing. So you must have enough energy, does that look like energy on the screen? Energy. And the correct orientation. And I'm a little surprised they didn't, little surprised, not a lot. They didn't put it in this one. I don't know if a list can have two things. Can a list have two things? I've heard people argue that it's not a list until you hit 3. Anyway, that says correct orientation.
Yes.
So a catalyst backing up lowers the threshold energy or the activation energy. Well, the threshold energy, the distance between the average and the threshold energy is the activation energy. So it's another way to say the same thing. So threshold energy, sure. So more molecules collide with sufficient energy. More molecules have the required threshold energy. They've got to give it to you, I would think. Anybody else on dot 1? Also, did somebody start to say something? Sorry.
Oh, no.
In 10 years, when you're writing the document for work, can you do everybody a favor and not just put dots? Every dot is the same. Number things. It drives me a little bananas. How did people not think of this? Stupid dots. Then you can say, I've gotten so many worksheets off the internet, and they go dot, 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 and now I'm trying to tell kids dot 5, and then they miscount. If it would be numbered or lettered, I could tell them. Okay, dot 2. Why does increasing the temperature speed up the reaction? It pushes this bump over to the right, which is another way of saying more molecules have more energy, so that when they bump with the correct orientation, they're more likely to react. Huh?
Can you repeat that again, please? My internet cut out.
Okay. On average, if you heat it, on average, the closing speed between the two molecules goes up. The energy with which they will collide goes up on average. Does that work?
Yes.
So if they have the correct orientation, let's just assume that for a moment, the chances that they will react goes up because they're closing on each other at a faster speed with more energy.
Oh, okay. I understand now.
Okay. Also, can we go to also?
Yes.
Because they're moving around more at random, the chances that they will have the correct orientation also goes up. If you're just going to bang them together 5 times a second, your chances aren't very good. Why don't you try banging them together 10 times a second? Your odds go up, don't they?
Yeah, if you banged them harder, wouldn't it?
No, not harder, more often.
Well, yeah, more often everything would go up.
Right. No, because it's at random motion, right?
Mm-hmm.
You're just throwing these down into a bowl and see which ones line up right correctly.
Yes.
Well, only a few a second, right? So throw it more times a minute. You'll get more done, won't you?
Yeah.
So if you can bang these together more often, your chances of getting them to line up correctly goes up. So if you heat it, step 1, if they have the correct orientation, they will have enough energy to overcome the threshold energy. But step 2, more frequent collisions makes more possibility of having the correct orientation.
Mr. Swaney,
Yep.
is it possible for the pressure to be so intensely high that you can't have like them rearrange? Does that make sense? Like if A was sideways, it wouldn't have enough room to spin normal.
I don't know if that actually ever happens. Is it theoretically possible? I don't know. I don't know. I'm trying to think. Even in the core of a star, isn't it?
Well, most definitely in a core star.
It's not.
Like a neutron star is so dense that the protons and electrons just come together.
Oh, that's why they make. Oh, that's right. That's why it's a neutron star, isn't it?
Yeah.
So the edges are the what's glowing of a neutron star. Not, but it's not really. Is the interior dumping energy? I don't know. Not questions that come up to me. You know, I think I should go in and type this in and improve this workbook. So step 1, the temperatures increased, so they're colliding with more energy, so they can more of them can overcome the threshold energy. That's pretty good. I got to admit. But step 2, also more frequent collisions creates more chance for a correct orientation collision. In case you can't read that. More frequent collisions creates more chance for a correct orientation collision. That's just my phrasing, but it works. Well, are we at the point of, first of all, does anybody want to back up to something? Because backing up now is better than backing up later. Okay, I will go till people need to drop out. I have a tiny suspicion that I'm going to get my brain is full. Also, is Annalee still here?
Yes, I'm here.
Okay. Just as, I mean, it's not required. Can't turn you in for being absent. But, you know, it's your tutoring session too, Annalee. Speak up. That's an encouragement, not a criticism. And the Arrhenius equation doesn't show up. So that means I want to go in and cross out some of those, those homework. These two use the Arrhenius equation, or this one certainly does. And then this one, I think that's the one where there's a very tricky math thing. So all you extra math people, give that one a thought. And I don't even entirely remember. I had to have one of the most math kids I've ever met actually show me what they were doing. And it's in my other notes, I think. Anyway, you know what? I don't care. It's not going to come up. They don't ask stuff like this. I don't think I've ever seen by something like, by what factors does K increase? And if it does, we'll get to it then. I'm almost positive it doesn't. And then I think this says lesson. This says lesson. Okay. So we covered that. There's lesson, which is that page is kind of half. Well, this part. We covered this mostly, or we have before. I can go back to it. This one. I mean, I don't care.
Yeah,
We
can
did
we go back to that one, please, just for like a refresher?
Sure. You want to just start at the top?
Yes.
Okay. What step is the rate determining step? 1 takes more energy to get done than 2.
Yes.
So this is the slow step,
Yep.
which is the rate determining step, right?
Yes.
So there are 2 steps apparently, and 1 is slower than 2. This is the rate determining step, step 1. If that's true, then, because here's the steps back on the previous page. And they said slow. I'm answering sort of the wrong question. I thought they were giving you the graph and saying which was the rate determining step. However, I will point out that's a legit question. To give you the graph and saying which is the rate determining step is completely fair.
Yeah, and will the graph look something like the one here?
Yeah.
All right, that's easy enough.
On the other hand, I do see that they defined the first step as slow. Although, if that's it, where's the third bump? Oh, no, sorry, this goes for that. Oh, okay, I'm sorry, I misapplied. See, when I read too fast, this graph is for that. I take it back. This graph does not illustrate that point. I take it back, sorry. How do I know that step 1 is the rate determining step? Because they said it's slow back here on the previous page. Okay.
Okay.
On the other hand, watch. In fact, this is what they're asking for example 2. Can we just start there, I guess?
Yes.
Example 2. They are giving you the graph and saying which has the slow step, which is the slow step. How can you tell? 1, because it has the larger energy of activation, which is what I was saying at the beginning. So this is the slow, and this is the fast?
Yes.
So then, what's the rate law? Easy peasy, lemon squeezy. For the purposes of the rate law, you can ignore the second one because the slow step is first. So it's just reactance times K, reactance to the power of the number in front times K. Look, rate law. Sorry, I was skipping down here. NO2 to the first times F2 to the first times K is rate.
Yeah.
I thought they would ask that first, so I answered it first. Write the overall reaction. Well, nothing cancels. Oh, yes, it does. F single cancels out, doesn't it?
Yes, it does.
So we have two NO2s plus F2 yields NO2F. Or two NO2Fs. Whoops. Two of them, huh?
Oh yeah, there would be two.
Which is why they are correct.
Okay. And then this one would be F.
And the intermediate is F because it crosses out because it's on both sides. It is created and yet consumed. That's just my little phrase. Example 3 then? Oh boy.
What is it?
Because it has the substitution. And usually that is the kind of thing that needs to be seen like 3 times. Do you want to do the substitution?
Yeah, I somewhat understand, but it's still like iffy.
Okay. Just open my computer to store all this video. Okay, so here we'll try to do it sort of more blind too, okay? So what do we have? We have NO plus O2 yields NO2 plus O. And that's the slow. And then the NO plus O single makes yields NO2. That's the fast. Oh, sorry. I'm writing the wrong thing. That's not even helpful. God, this is what happens. I'm telling you, I read stuff, it's too fast. Let's answer the real question. This is the overall reaction. The rate law found through experiments is found to be this. This is the real rate law, period. They did the experiment. They did it 100 times or something, and this is the rate law, period. I don't care what else you can say about it, and you can argue about the mechanism, but by God, that's the rate law. They did it through experiment, right? There's no arguing with it. This is the real rate law. So if you come up with a mechanism system that doesn't generate that rate law, your mechanism has to be wrong. Does that work?
Yes.
So person 1 says, I have a mechanism to propose. And you say, but slow comes first. So therefore the rate law is just reactance to the power of the number in front times K. It's this?
Yes.
But this is not that. That is wrong. Then your mechanism is wrong because it gives a rate law that I know for a fact is wrong.
Okay. I see where they're going with this now.
Your mechanism does not generate a rate law that I would bet you $5,000 is correct. So your mechanism cannot be wrong because it generates an incorrect rate law. Okay?
Mm-hmm.
Okay. So that's 1. 2 is where I wanted to write all this stuff down. 2 is NO plus O2 is in equilibrium with NO3. And then NO3 plus O2 yields 2 NO2. Double checking. NO plus O2. 3. NO3 plus
NO2.
I wrote it wrong. Plus NO, right? There we go.
Yes.
Okay, so good. This is why we double check things, right? Everybody else looking, I wrote this right? I think so. Okay. So, but this is fast and this is slow. Also, you could tell because there's no way this could be the slow and set up an equilibrium, by the way. But also they said fast and slow. Or they could tell you fast and maybe make you figure out that it's at an equilibrium. Anyway, so the rate law, so the slow rate law, that's just my own phrasing. The slow rate law is rate equals, right? rate equals K, whatever that is, times NO3 to the first times NO to the first.
Slow. Yes, that would be the slow rate law for mechanism 2.
Right. It's the slow rate law, but it's not the real rate law for mechanism 2 because the slow comes second. This is where the math gets tricky. But NO3 is not an original reactant. It's supplied by the previous step. And I was saying that if the fast step is first, that just for stupid numbers that I'm completely making up, you're making 8 of these and only using 3 of them. This stuff's building up really fast, right?
Mm-hmm.
You build up so much of it that it doesn't know what to do with itself, and it's not perfectly stable. It has a tendency to tear itself apart back into the reactants. That's why the arrow also goes left. Can it fall apart back to these? Oh, yes. And if you build this up far enough, it will do it. And if you build it up far enough, it will do it at an equal rate to the rate you're building it up.
Oh.
Which would probably happen pretty quickly, frankly. This builds up, builds up, builds up. As it builds up, it starts making the left side. It builds up far enough, you're tearing it apart as fast as it gets made. And then you have an equilibrium. That's a key point here.
Okay.
Anybody need to repeat on that part? Thank you, Naomi, for all the questions. This is good. Feel free to chip in, Annalee.
Yes, can you repeat that real quick?
Yeah. This stuff is making, these reactants are making this reactant. But this process isn't chewing up this stuff near as fast as you can make it. And I said for my stupid numbers that I completely faked, we're making 8 of these a second and chewing up 3 of them a second. This stuff's building up, isn't it?
Mm-hmm.
Well, every time you make one, it has a certain tendency to fall apart and go back. Well, you build it up enough, and enough of them are falling back, creating the left side, that they equal the rate that you're even creating them at all. So if you build these up high enough, I said, these are falling apart at 8 a second as you make them 8 a second. Or, well, you said we're chewing 3, right? Okay. You're making 8, chewing 3, leaving 5, right?
Mm-hmm.
But 5 of them are rolling back and becoming this. So it's actually, you know what it is? It's basically more like this, I think. You're making 8, eventually this builds up so much that you're basically using, like, you're rolling back 7.99999 and the other tiny bit goes here. So you're making 8 and essentially chewing up 8. It's really close. Essentially, you get to the point where this is falling apart just as fast as it's being created. And that's why it's in equilibrium. The rates forward and back are equal.
Okay, and to clarify, when a step is at an equilibrium, it cannot be the slow step.
It wouldn't be the slow step. That's true. Because the slow step doesn't. Let's see here. That's a really good point. Why exactly? Okay, to be picky, yes, you could build this up to where it goes back, but we're not going to talk about that right now because it's assumed that this is not going to build up fast enough to really to beat this. You know, it's a decent point. Can I kind of ignore your question because you kind of you stumped me a tiny percentage on that one?
Yeah.
Good job. Good job. Stumping me is good. It means that you're using your brain, right? Often also, this gets removed in many reactions. It's a gas and escapes. Like these are aqueous and that's a gas. Well, then the bubbles come out and it can't go back, right? Because it left. Or it creates a solid. Or, Well, even those can go in reverse. But anyway, can we skip that for right now?
Yeah, sure, that's all right.
So this has a tendency then to run backward. If you get to equilibrium, and you will, it will be true that K for the equilibrium is equal to products over reactants to the power of the number in front, products over reactants to the power of the number in front. You're going to hear that to the point where somebody is going to wake up and the second thought through their mind is going to be products over reactants to the power of the number in front. Somebody's going to fall asleep and hear me say that in the back of their mind. So it's going to be NO3, and brackets means molarity. And it is very much the molarity that counts here. Or there's also a pressure version, but to the first over NO single NO to the first times O2 to the first. And I don't know who discovered this, and I still don't understand exactly how you would figure this out. I have just taken it on faith that very, very smart people tell me this. Okay, sure. Does that work so far? About this
Yes,
part?
that works.
Okay, here's the trick. The NO3 in the slow step that I was here, right, is being supplied by the NO3 here, which also sits here, right? Well, here's the thing. Here's the real thing. Here's I don't know if I explained this well enough, and that's a good point. So I'm glad you guys are asking questions. Questions are good, right? You can't have a rate law with a reactant that you didn't even supply. That's the real problem here, to say it as clearly as I can. This rate law is sort of true. Well, I wrote it, you said reactants to the power, the number in front. Yeah, right. But this isn't really a reactant. When you poured this stuff together into a beaker or whatever, I know O2 is a gas. Shut up. You can't, I know. But when you stuffed these things together, was there any NO3 there? No. The NO3 was created by you putting these together, right? So what you want is a rate law that reflects something you can use, that reflects the reactants that you're actually using. I'm only using this. Everything else here is out of my hands. From this point on, I'm not controlling it, right? I can control this amount and that amount, and everything else is nature just pushing stuff. So a rate law that has an intermediate is no good. And I would put note to self. In fact, I want to type that in. I'm going to write that down so I remember to add this in. A rate law with an intermediate is ineffective, useless. I'm going to say useless. So we have to get this NO3 out of here. How can I do that? Well, we need to use the original reactants.
Your camera is a little blurry, Mr. Sweeney. Can you repeat that for me?
A rate law with an intermediate in it is useless. And I tend to write at an angle here. We need to use the original reactants. Is that more legible also?
Yes, thank you.
So I got to get rid of the NO3, and I got to get it in terms of NO and O2. But look at this. If I solve for NO3, do I get it in terms of NO and O2? I do. So let's do this. Let's solve for NO3 and then take that equivalent and put it in here. So isn't it K NO2 is equal to NO3? Yeah. I didn't put EQ. No one cares, by the way. It's assumed. That means that I can take this and substitute it in for NO3, can I? They're the same thing, aren't the equal sign means same thing, doesn't it? Therefore, I have rate equals K. Here, if we do K1 and K2, K1 times K2 times NO times O2 time, now this goes in there, right? Times NO. I don't know at what speed to go. I don't know if I'm going too fast or what here. So I think I'll hit pause and wait for somebody's question or something.
And we're doing all of this so we could substitute to find the rate loss.
The real rate law has to be in terms of the original reactants. And if you do the slow step, if you only do it where the slow step is second, like this, it includes an intermediate, doesn't it? Because it's created and yet destroyed.
Oh, yeah.
So you got to get the intermediates out of there. A rate law with an intermediate in it is useless. We need to use the original reactants.
Okay, so we're doing all of this to essentially get rid of NO3 so we can...
Very much.
Okay.
So we can express the rate law in terms of the original reactants only. So when we consolidate this, a constant times a constant is just another constant. I don't care how many times you take 3 times 6, it's 18, right? So a constant times a constant is just another constant. And you can call it K3 if you want, it doesn't matter. But just for the illustration purposes here, I guess I will, just to show that I don't mean that it's the same one. I mean, it's a third number, and yet it is a constant. And I never quite know if that makes sense to kids right up front. That's what I was trying to say. If you take 6 times 3, you always get 18. So why not just write 18? I mean, I guess you could write this, but it's a waste of time. Why not just put in the answer that you know? And then NO times NO is NO squared. And then times O2 to the first again, right?
Yes.
Whew.
Oh. That was a lot, and I feel like I just need practice with it, but I understand it now.
Okay, I would go back and try this one again because that's. I wish somebody had said this out loud to me. I sort of just figured it out. Oh my God, I think I know what they're doing. I'm going to try it all on my own. Because sometimes I thought I did, and if I had left right then and said, well, that's solved, close book, go home kind of thing, I wouldn't have discovered that really I forgot how they did that one part in the middle. So I would say try these substitution rate laws until, and this is a general thing for all time and space on studying something, try it and ask questions until you go, oh my God, I actually feel a little dumb. It seems so obvious now. I could teach anybody to do this. Well, then you know you've got it, don't you?
Yes, that's how you know you have it.
I mean, I guess it's possible you don't get an A after that, but, because you see all the dumb mistakes I make, but, you have arrived when you feel like, oh, I could stand up at the board and teach 5 more people to do this. Then that sounds pretty confident, huh? So this is the final stupid rate law. It had better match or I'm going to be very angry. Look, K n O squared O2 to the first. Told you. Mechanism 3, the slow step is first. So all you have to do is go, a reactance to the power of the number in front. The rate is K n O squared. Wait a minute, isn't that what they said? So it's consistent with the experimental rate law. Mechanism 3 is correct.